Good morning. So I'm gonna finish up this chapter, chapter 10 on virtual memory. So this is where we left off last time. We're talking about frame allocation, and that's the problem of what pages or what frames do you assign to each process? Do you assign one set just for a given process, and the process may use only that set, or do you allow a process to grab a frame from another process, right? And even if you allow each process to only get its own set, do you assign equal number of frames to the process or different, right? There's different variations. Global replacement is one where a process is allowed to take a frame from another process, right? And so we saw the trade-off there. More flexible, better utilization, and that's the more common way, but it's less predictable. Whereas if you limit a process to only its local set of frames, then yes, it's more predictable behavior, but then it might not be a good match because the number of frames that the process needs may differ, may vary over time. And so that is probably not as good with memory utilization or frame utilization unless you can somehow adapt that to the demands. Now, there's also what's called major page fault versus minor page fault. And what does that mean? So a major page fault is where you get a real page fault. That is, you want a page is not in any frame, not in memory. You need to bring it from a disk or backing store. Now, a minor page fault is where you get a page fault, but even though a frame is already marked as free, you haven't wiped out its content, and you keep track of where that frame is and its state. So you say, well, okay, I already marked some frame as free, but I haven't wiped it out, and it's kind of like you put it in garbage, right? In the garbage can, you haven't emptied the garbage can yet, and then you say, oh, I need that page which maps to the frame. The frame is still intact, so you grab it out of the garbage can, right, or the recycling can, so to speak. And since nobody touched it, it still has it. So that way, you just have to bring it back or rescue it from the free frame list and then assign it, right? So and just update that. And so that way, it's called a minor page fault. So because of a little bit of tracking, you don't have to go and fetch unnecessarily from the disk, right? So that's only if you have a way to track something in the free frame list without wiping it. Now, so that happens when you have kind of a background process that is somewhat aggressive at reclaiming pages, okay? Or what I should say is it's kind of like an aggressive recycler. It will go around and periodically and just ask each process to give it to release some frames, okay? And then so why is that? Because the purpose is to keep the free frame list from becoming empty or from dropping below a certain number of frames. So that way, when it comes time for page fault handling, you always have at least one, if not more, the free frame to choose from. So you can think of it as shown in this illustration. So there is a maximum threshold and minimum threshold. So when it drops, the number of free frames drops below, or I should say it could be a free memory, or it could be a number of free frames, drops below a certain threshold, then it triggers the Reaper. Reaper would then try to apply certain page, or I should say the replacement policy, find some victim, even though the user program hasn't demanded it yet, right? A demand paging wouldn't do this until you actually need it. But Reaper would be a little bit more aggressive and saying, even though the program hasn't demanded it, I'm still going to go around and grab some and find some victim, put them on their frame on the free frame list, so that I have something. I keep the number of frames, free frames, at least at some minimum. And once you get enough, then it doesn't do it, right? And then, but it actually goes up to a maximum threshold. So it'll continue activating until the number of free frames or your free memory hits above that high threshold. So you may have seen this. This is called hysteresis. Or in EE, you may have seen what's called Schmidt trigger. In other words, it's one thing that has two thresholds. A low threshold to trigger it, but to stop it, you actually need a higher threshold to stop it. Okay, so the Reaper would continue operating even though you already got beyond the minimum threshold. It wouldn't stop until you hit the high threshold. Then you could continue using until it drops below, if ever. Then it gets activated again. So the Reaper is activated from the time from A to B, and then it stops. Once it hits maximum threshold, it actually could go above because somebody might voluntarily return these free frames, right? But it wouldn't run again until it drops below, and then that's when C. And because these are actually sampled, so once every 100 milliseconds or so, or 10 times a second, you actually could drop below your minimum threshold by a little bit more. But the hope is that you set the threshold so that it never hits zero, right? And so then that gets triggered, and the Reaper runs between C and D, and then after it hits D, or it goes above, then Reaper stops, and it wouldn't get triggered again until the free frame list drops below that minimum threshold again. Okay, so you can do this even without demand from the program, and it does so to maintain this kind of the low watermark on the free frame in the free frame list. And how do you do this? Well, a lot of times you use what's called second chance, but then you could also pick what's called FIFO when the memory drops really, really low. Why? Because at that point, you're somewhat desperate, right? So picking out any page is probably just as good as any other page. By that time. So FIFO just makes it kind of fair. Everybody gets a turn getting kicked out. Okay, so that's what Reaper does. Now this is related to thrashing, and I mentioned thrashing last time as well. So what's thrashing? Thrashing is a state in which a process is busy doing nothing but swapping, or swapping pages. Why would that happen? Well, when it doesn't have enough frames, right? So it uses up all the free frames, and then it needs to bring in some more memory that is not resident. But to do that, it has to kick out one of the frames. So if you do fixed allocation, that actually happens even more, right? Because you're limited to only a set of frames. And if it doesn't get enough, then has to find a victim. It's probably one of its own victims, right? So one of the process's own pages gets replaced. Okay, so that allows you to bring in the page you demand. But then pretty soon you need that page that just got kicked out, right? So then you spend all your time bringing in page, well, kick out one, bring in another one, kick out, bring in, kick out, and then each one is very expensive, right? And so that is thrashing. Why? Because it's not doing any useful work. It's all the OS time spent bringing pages in and out, memory in and out, in and out. And I don't know if this ever happens to you, but it could really happen when you run on a machine that doesn't have enough frames allocated to a process, or doesn't have overall enough physical memory, right? And it relies on the paging to disk and back to implement this abstraction of much larger memory, right? And this is a vicious cycle. Why? Because what could happen is if you recall from last time, during paging, what happens? The OS actually does a context switch, right? Let another process run. And the idea there is, well, hopefully that other process has all its memory resident, right? But what if that process also gets a page fault? Well, it gets queued up, right? And then the OS initially may have a limited degree of multiprogramming, but it says, oh, all these processes are waiting. That looks like I/O to me. So let me increase the degree of multiprogramming by running even more processes. But what happens? Then each process, additional process you bring in or enable or increase your degree of multiprogramming, it demands even more resources, right? So that's further competing against the already lacking resources that you were having, or memory resources to be specific, but other resources as well. So then you add more processes, and then it just gets worse and worse, right? And then it could really bring your machine to a halt, right? And occasionally that happens. I mean, at least on my machine, if I have too many things all running, and each one can take, especially like Chrome is really a memory hog, right? If you run Chrome and run some other things, and you have like lots and lots of things all going on at the same time, it actually could pause your machine in a way, like it's stuck. Not you can't do anything. And then if you have a disk that you can hear, right? It's just disk is spinning, very busy. Well, it's probably when it's thrashing. Okay, so thrashing is a really bad situation to be in, and OS should do something about thrashing. Otherwise, it really will take a really long time for it to get out, and it's not productive at all. And so, as you can imagine, right, if you increase the degree of multiprogramming, you increase CPU utilization, but up to a certain point, when the memory demand increases, then becomes thrashing, and CPU utilization drops. Why? Because it's doing nothing but swapping pages in and out, right? Correct. Depending on how you allocate your frames, right? You could temporarily suspend the other ones, grab the frames from one process, give to this other process, then it has enough. Then once it gets beyond this high demand, its demand drops, then you resume the other processes, give them more frames back. Then that way, it may be one way to get unstuck, right? So it's not exactly deadlock, it's kind of deadlock because they grab each other. I mean, they still make progress, it's just extremely slow, okay? So if you don't give them enough frames, they can't make progress, simple as that, right? So they are making progress, just very slowly because they're fighting against each other, right? And so that's when the CPU utilization drops, and why? Because it's all I/O, right? And then, so that's when thrashing. So that means as if your processes are running at a very slow clock rate, because effectively that's what it's doing, right? And so what can you do? Well, so the whole point here is really the concept of locality. Locality, there's two kinds of locality, temporal locality and spatial locality. You probably have seen this from your architecture class, right? That's how caches work. That is, if your program tends to exhibit certain behavior where if you use a piece of data, you're likely to use it again. That's soon. So that's temporal locality. And the spatial locality is if you use a piece of data, then its neighbors in memory are likely to be used soon. So based on these two kinds of locality, that's how caches can work. Now, demand paging has a somewhat similar concept. And so, but it has this concept of the set of, you might say, memory locations you may be using in a particular time window. Okay, and that's what your locality is. And a program, you can think of it as migrating from one locality to another. So for example, when you're starting up, you might be initializing a bunch of global variables. So that global variable region might be your locality, right? And then as your program runs, maybe it dynamically allocates a bunch of objects, right? Especially object-oriented class, or if you load in some file, then parts of your file, like you think of it as user editor, right? Text editor or word processor. When you're editing, you're probably likely to be working on a paragraph at a time, or a few, maybe small part. And so if it's at the bottom of the document, probably won't be looking at that, right? So that you can safely put that out if necessary. But the part where you're actively working on, that's your locality, right? And if you do selection, copy, and paste, right, your locality, depending on how much you select, that could be a lot, maybe entire document, or maybe a few paragraphs or a few words, right? So your locality could vary. So if you select the entire document, that actually increases your demand for memory, right? And so as you can see, the locality varies over time, just depending on what the program is doing. And sometimes you use early part memory, middle part, end part, something bigger chunk, smaller chunk, right? And so the pager may not be aware, most likely, this is only application knowledge, right? And the OS probably doesn't have a lot of knowledge other than the fact, oh, you're touching this page, or you're touching that page, right? And that's really the indirect knowledge it can get. And so thrashing occurs when the sum of the size of your locality is greater than your total memory size. Or you should say the locality, this is actually sum across different processes, right? And or if you have local allocation, that can do good things or bad things to thrashing. Why? Because it actually is better to prevent thrashing, because what can be thrashing is limited to that process. That process is not making a lot of progress, so that means OS can context switch to another process. As long as these other processes are not thrashing with their local frame allocation, then that can make a lot of progress, right? But then when it comes back to this little local allocated process, then it could still continue crawling, but then that is, well, at least the whole system wouldn't be brought to a halt. You might just have some processes that making very slow progress, but the other ones are going to be fine. Okay, and so using some kind of local frame allocation may help limiting the effect of thrashing, so the entire machine wouldn't be brought to a halt. Only certain processes would crawl. Okay, now priority page replacement could also help, but then that requires the OS to be able to identify which process is likely to experiencing the thrashing effect. Then prioritize certain ones to get unstuck. Okay, so here is a picture from the textbook showing locality in memory reference. Okay, so how do you read this? So the way you look at is the page numbers, right? So and so the vertical axis shows the parts of the memory that gets touched from page 18, 20, 22, 24 up to page 34. And then you see over time. So initially, not a lot. And then somewhere here, wow, it's pretty intensive. Right here, right there, a little bit, but then here, nothing, right? And then, so it continues doing that. This part goes away for a while. This shifts a little bit. This intensive part gets shifted up, right, over time. This part presumably global, so it always gets accessed a little bit. And some parts never really touched, right? So as you can see, sometimes these, each one is a page, right? So some pages never get touched for a long time until later. Then, okay, then when it's working on the locality now shifts over from page 24 to 29 or so, right? And then there's some parts free, and this part used to be very active, now not active at all. And so then I snapshot Okay, so A and B. So A, you can think there's one locality here, another locality there. And then B, one part, and then B, there's this part, and then a little bit on top, right? So that gives you an idea. This is presumably from a real memory reference trace. So helps you visualize what happens to memory usage, and that. So depending on how you do your paging, it could make a difference as to whether you get into thrashing or not. Okay, so the book talks about working set model, but they don't go into enough depth, so I'm just gonna talk a little bit about this, but I'm not gonna go into too much. In a more advanced OS course would have more to say about working set model. So you can think of it as the working set window should be a set of a fixed number of page references in a time window. Okay, a time window may be say 100,000 instructions, and so so that's the page references. Remember, page reference would be like last time would be the reference string, remember? So that would be just the page number. You don't care about the specific address as long as it's within the same page, because that's what matters. That's the replacement granularity. So working set of a process P sub I is denoted WSS sub I. That's the total number of distinct page references in the most recent window, okay? And that can change over time, as you saw. So if your window is too small, then it will not encompass the entire locality. But if your window is too large, it encompasses several localities. And if the window is infinite, it encompasses the entire program. Okay. And so the working set model can be used to help you determine the locality as well as the thrashing condition. So if you sum up the working set, so WSS is a working set of a process I. So sum up the working sets of all processes, that's the total demand, the total demand frames. And so that approximates your locality, right? Because you're still doing the page granularity. If the total demand is greater than your number of available frames, then you get into thrashing, right? So this is summed up across different processes. Now, so what can you do? Well, then what you can do is you would either suspend or swap out an entire process, not just its pages, right? So that means you don't even try to schedule or context switch to a certain process. You don't even run it at all. You just want to get it over with so that you allow one process with high demand to be able to just get it done. Then hopefully those frames get freed up. And this kind of reminds you of how these deadlock algorithms work, right? Remember how deadlock actually is more in terms of, okay, well, if I just can't get it, I don't make any progress. Here, you just making very slow progress. So if you can satisfy the demands of certain ones, then they actually can pay back big time because they free up even more frames to you, which you can do to service the demands for the other processes, okay? So really, to resolve thrashing, what you can do is really not increase your degree of multiprogramming. In fact, try to suspend certain ones, almost like, so process swapping is almost like resource preemption in deadlock resolution. Remember one of the ways to do it, right? So by essentially swapping out, you free up its resources, kind of like preempting its resources, right? And then give that to this other process, then it has its memory demands is more likely to be met, its page falls is likely to drop. It goes through more efficiently. Then that's when you can bring back that other process, right? Swap that other process back in, and then try it again to see. Hopefully, you get a better chance of finishing. Okay. So this is an illustration of how the working set can transition. So the page fault rate increases and then drops, right? That's just depending on the demand, and then this can increase again and drop again. So working set is defined to be from the start of one peak. So that means it's not that the peak, it's the start, right? So that's when it starts rising to this peak. That's the start to the start of the next peak. So that's what a working set is if you try to visualize it, right? Now, page fault frequency is another way, we might say a more direct approach compared to the working set model. So working set model, that was a way for the pager to figure out what if the system is thrashing, and then take some action. Whereas page fault frequency is more like you doing a count of how many page faults has occurred in the last so many reference. So it's more of a percentage, right? And then so you can think of it this way. So if every reference you're trying to make, it results in a page fault, or 99% is page fault, you're thrashing, right? And so that's actually a very direct way. You don't even have to bother doing with this working set model. And so then what happens is then you again set some threshold, right? That's some acceptable page fault frequency, and use that to determine whether you need to adapt the number of frames you allocate to a certain process, okay? So if the actual rate is way below your lower bound of the page fault frequency, then what does that mean? You probably allocated too many frames to this. It's not taking any page faults, right? Then that means I can probably afford to steal a number of frames and give that to some other process that may need them, right? Or if one process gets page faults more often than your upper bound, some upper bound, and then that means maybe it needs more frames. So I hopefully balance this out, and so by giving it more frames, I have more chances of reducing its page fault frequency, right? And well, remember that there's a Wiley's anomaly, right? By giving it more frames doesn't guarantee it's going to lower its page fault frequency if you use a FIFO type of replacement algorithm. But a lot of other ones, LRU and so forth, those will not have the Wiley's anomaly. So yes, in practice, giving it more frames does help reduce its page fault frequency. And this hopefully will work so that you don't even get into the situation of thrashing. Okay, so by checking this, then it already adapts over time, and hopefully your working set doesn't change so rapidly that this allows you to amortize the cost over time. Okay. Okay, the last topic of this chapter is quite different. It's allocating kernel memory that must be physically contiguous. It's like, really? Why? Oh, yes. That actually is a very special requirement for kernels. So remember we talked about the benefits of paging is so that you allow the user program to be logically contiguous in memory, but then physically they are scattered, right, in different pages. But can you do that in kernel? It'd be difficult. Why? Because the kernel is the one that's implementing this abstraction, but for the kernel to be using paging, that's actually asking for a lot. And because why? Because it's already running in kernel, and you get a page fault. Where do you trap to? You're still in the kernel, right? So in OS, you probably don't want to have. Well, it then becomes recursive, right? And so you really don't want the kernel to have to deal with that. You want the kernel to run very efficiently. So that's why having physically contiguous allocation helps a lot, so that you don't have to ever deal with the problem of implementing yet another abstraction to have physically contiguous memory. Okay, so why kernel would need more contiguous memory? Well, in particular, all these buffers and these data structures, right? So let's say buffer. Okay, so buffer, I/O buffer, depending on the device, could be your network TCP/IP, your network interface card, could be your disk, right, and a certain block size, right? These have to be contiguous. Why? Because it's not just a processor that accesses the memory. You have DMA. DMA is a controller that also has access to memory. In fact, the processor can set it up so that the processor gets out of the way. DMA can steal cycles from the processor when you're not accessing memory. DMA say, oh, I need to fetch something from the memory buffer to the disk, or I have an incoming packet or incoming one that I'm going to dump directly to memory. When it's done, generates an interrupt, kernel goes there and fills it. So that way, kernel doesn't have to doing byte-to-byte transfer, right? That's very slow. A DMA controller does that. But then, remember when we were doing the paging, you needed an MMU. MMU, where's the MMU? Well, it's associated with the processor. The DMA controller does not touch the MMU, does not go through MMU. It goes directly to physical memory. That's why it's important for this abstraction. And it's way too expensive for the DMA controller or other I/O devices to have to go through DMA in order to access memory, right? So this interface from device to memory, that part has to be done in physical space. That's why the kernel needs to work with physically contiguous memory. Besides, kernel has its own data structures too. What are some examples? You have semaphores, you have PCBs, right? Process control blocks. Later you'll see file control blocks, some control block, this control block, that control block, lots of different control blocks, right? And these are structs. And you know how a struct is implemented? Well, most likely it's written in C, right? You know, Linux is all in C, Unix written all in C. Most things are all written in C. And so in a struct, what do? Well, struct is really, you can think of it as a contiguous chunk of memory. And you have a struct dot some field name, right? You have a struct, and then like your length is a field, the buffer is a field, and the process ID is a field. What are those fields? Those are really fixed offsets from the beginning, right? So a struct is a lot like a pointer to the beginning. And if you have a field, compiler already lines up the memory within that struct and knows, oh, this process ID is offset 16 from the beginning, right? So when you do something dot a field, that looks like base address plus a fixed offset. And you've seen that kind of addressing before, right? So that way you can do it. But that works only if the memory really is contiguous. If the memory is not contiguous, then that abstraction breaks down, right? So the compiler can no longer generate a base plus offset type of access to such a struct, such a control block, right? And if you see kernel data structures, they are nothing but these structs in C. So that's why these kernel data structures must be contiguous too, so that the generated code in terms of the struct field access can also be done correctly. Otherwise, every little field access turns into like another 3 or 4 times as many instructions to do, right? In order for the compiler to do that. That's just not worth it. So the kernel code has to be really, really lightweight, very streamlined. So having that ensures your kernel can perform its task using the most efficient possible code. Okay? So what can the kernel do? And it can't afford to do that kind of general memory allocation. I mean, have you guys done that programming assignment I gave for the last chapter? There was a malloc and free. Please say yes. If you ever did that, then you can see how easily you can create holes, right? You have one data structure, and if you just use heap, then it creates a hole, and then you give it back. It's not in the same order as your allocation. It's not like a stack. So next time you free, then a hole, you can have big holes and little holes everywhere. and it's going to be a mess. And sometimes when you're free, you actually have to go back and see, can I consolidate or coalesce these holes together to make one bigger hole, right? And so that is a pain to have to deal with. A kernel can't afford to do that. I mean, if you really implemented the algorithm, and I really encourage you to do it, you get a real feel for, wow, this is how much work it takes to manage dynamically allocated and deallocated memory. It's a lot of work. Okay, please just spend some time. I gave you all the hints in there. Just write it and try it. And so a kernel really can't afford to do that, because every time it does it, it may have to do the worst case, order n, just scan through everything. Okay, even for the first fit or whatever, right? I mean, best fit is already ordered in. First fit, if in the worst case, still ordered in. So a kernel can't afford to do that. Kernel overhead is just it has to be limited. So what are some strategies? So there's one called buddy system, and that was more simplistic, but it has a little more limitation. And slab allocation, that is done to be a little more efficient, and there's several improvements over the slab allocation, slob and slub, all kind of similar sounding, but they do something different. Okay, first, a buddy system. So it's also called a power of two allocator. What does that mean? That means you have contiguous memory. It should be a power of two in terms of the units you care about. And then every time you allocate, what do? Well, you do kind of a binary search, right? First, divide it up in half. Oh, first, is this the best you can do? If your memory takes up more than half the memory, well, yes, you allocate the whole thing to that data structure, and that's all. And then, but if you don't need the entire memory, can I do half? Okay, if it fits in half, can I do it in a quarter? So you do a binary search on this size, right? And so you allocate a chunk that is the smallest power of two that's big enough to fit that request, okay? So say if you allocate, I request 28 bytes, what's it going to allocate to me? Well, you can allocate 16, but 32 fits, right? 16 is too small, 32 works. So 32 is the smallest power 2 that can fit this one. So then you allocate a chunk of 32, which is a power 2. And so it does this kind of rounding up to the next highest, next power of 2. And so it keeps doing the splitting. And then it keeps split the current chunk into buddies, and so forth, right? And then you continue until appropriate size of chunk is available. And so that's how it works. So here is an example. You have 256K, and you can do a split into 128, 128, and 128 can be split to 64, 64, 32, 32, right? So then so what's the benefit? Well, if you remember, or if you tried the malloc and free one, you notice there's one part where you need to combine several adjacent holes together. Okay, so I allocate free, and so that's actually to carve out holes. But then if you free, and then you happen to be freeing some part that is next to another hole, you actually need to combine them to say, now I have a bigger hole, right? Instead of saying I have 3 little holes there, without realizing, hey, they're next to each other. So you could actually serve a much larger request. So that's called coalescing. With this buddy system, coalescing can be very quick, right? Because you just check your neighbor. Are you free? I'm free. Yes. Okay, combine. Now suddenly you have a double size. And then once you have double size, you check with its neighbor. Are you free too? Then so it's a log-in time to coalesce rather than possibly linear time. Okay, so this has the advantage of coalescing in log-in time. So that's desirable. But what's your problem? Well, you can imagine fragmentation is a problem, right? Because you're limited to sizes that are powered of 2. So it could be internal fragmentation, because once I give this chunk of power of 2 to you, even though you don't use up the entire memory, I can take any remaining part and I'll give it to somebody else. That's not possible. Okay, and so fragmentation is a problem. That is really not used as much, even though you should know about it. Slab allocator is one where you have one or more physically contiguous pages, and the slab will be big enough to contain one or more instances of a given type of kernel data structure. Now, so that's a slab. So it's on the order of, on the granularity of multiples of contiguous pages. Now, a cache, on the other hand, could be several slabs, one or more slabs. Now, different slabs in the same cache may be discontiguous, maybe in different places, but each slab has to be contiguous and as multiples of pages. Okay, and why have a cache? Well, because a cache, you can think of it as kind of a factory for a particular class of objects or a particular type of data structure. So a cache is where you can allocate a data structure of a given type, or free, you put it back. Okay, so this cache is a different sense of cache, like a processor cache. No, this is just a term for a container. Then so you may have one type of cache for your process control blocks, PCB, one type of cache for semaphores, one for file descriptors, which is also a struct, right? And so when you need to allocate one such thing, like you create a process, you need a PCB. You go to the cache for the PCB, say, please give me one, and so it gives you one, and then you can use it. And when you're done, put it back, okay? And so these are called objects. Objects are instantiations of data structures taken from a cache. But then where does the cache take it from? Well, it goes to a slab to get the memory, okay? And in the worst case, one slab is the size of one data structure, okay? But hopefully, you can fit several of them to minimize your fragmentation. Because this, after all, this is on page multiples, right? So now what you do is you pre-initialize these caches filled with objects that are marked free. So their boundaries are already known. And so when you need to allocate one, well, it's like a free list, right? Like free frame list, free whatever list. And because it already knows the type, it knows the size, it knows where to find one pretty quickly. And so that's how you can do allocation, deallocation very efficiently. It doesn't have to scan the different holes. It already knows which is free or which is not. And then you allocate somebody, mark it as used, so then you wouldn't reallocate it to somebody else unless it's freed again. Okay. So this is a way to visualize this. Now you have these slabs, and the cache can contain one or more slabs, and each slab is a contiguous chunk of page multiple memory. Right? Okay. So then cache would then say, okay, which slabs do I have? And the kernel objects would fit in at least one. So a slab should be big enough to fit at least one object, hopefully multiple, right? And then so that's. But then it doesn't go to slab directly. The cache takes care of which slabs to track. And then it only requests the cache to give it objects. Request allocates, request allocate. And then they may be on different slabs, but that's okay. And then there would be a separate cache for these 7K objects, okay? And so same idea. These slabs would then each one be a physically contiguous number of pages, right? And then gets a request, and then caches would track them. In fact, if a cache runs out of slabs, it could allocate more slabs, and so that way the overhead is minimized. And hopefully you start out with enough, and you never have to do that. But you can still do that, and you hopefully wouldn't have to do it too often. And because you already know the size of the objects, that should be a pretty efficient operation. Right, so a slab is given of a given type is full of use objects. Then it needs to say, okay, well, do I have another slab I can go to and then allocate objects from there? So pre-fills them, pre-initialize them, so their states are all known, and then you can quickly allocate the allocate. And when it runs out of all the slabs it has, well, go allocate another slab, and it adds that to the cache. Right? So this way, there's no fragmentation. Well, that's the book says no fragmentation. It's minimal fragmentation. At some point, you might not be perfect in fitting every single byte of the page, but close, right? Now, granularity is objects, and they're packed as closely as possible. It's not page or body chunk. Well, at some point, you still want to pack them in some multiples of pages. And that way, it's minimal fragmentation. Okay, so not like body chunks, which are forced to be powers of 2. The fragmentation could be severe. And this fast memory request satisfaction, yeah, that is definitely very fast. Recycle object memory through the cache. Okay. Now there's different versions of this. Slab used to be used. Slab is so from for a while, for about 1999 to 2008. That's what's used most. So Solaris type allocator, and it's supposed to be cache friendly. And this cache is a processor cache, and also benchmark friendly, and that was used in Linux. And before then, there was something called SLOB. Simple list of objects. That's what SLOB stands for. But it sounds, the SLAB, they all sound similar. That was used in Kernel and Ritchie KNR allocator. So for small, medium, and large objects, so it doesn't have as many different varieties, but that was the original idea, and SLAB is more a refined version of SLOB. Now SLUB is the replacement for SLAB, and so there's different ways to view this. So it has unqueued allocator, simple instruction cost count, better debugging support, and defragmentation, and so forth. But I'm not going to test you on the details. I think SLAB is kind of that idea you should take away. The other ones are more variations and optimizations. Okay, so finally, I want to touch on program structure, because for now we really have only focused on some demands without examining more closely to the program structure. So the way that a program, especially these scientific programs or sometimes machine learning programs, they may behave in a way, certainly cache friendliness is a big consideration, or memory friendliness. So if you take an architecture, they have these pipeline or banked memory, so they are aware of the architecture, the access pattern in these loops, nested loops, accessing over large array data structure, matrix data structure. That can make a difference, right? So they have the concept of strides, how you schedule the instructions so that you can make the memory access as streamlined as possible. Now, this also goes up to the next level, because it's not just the processor, right? It's not just the memory banks. Now you actually have to deal with virtual memory as well, right? And back to the working set. If they are scattered over different pages, then that puts a strain on the operating system. Processors only assume it's memory resident, but OS is responsible for implementing abstraction when you don't have enough physical memory for the virtual memory. And these scientific programs, they work on these huge data structures. I mean, think of it like these astronomy, right? Billions of stars or particles, right? All these, and so they tend to be really large, and you have to track individual ones. Or like for graphics rendering, right? You do shading, you do ray tracing, all those, right? Those are very large data structures, and so if you're not careful, the same program, if arranged differently, may cause different page faults. So like here you have row major versus column major. So by doing J in the outer loop, I in the inner loop, and how the data is laid out, you may have 16,000 some page faults. But if you switch the I and J, you accomplish exactly the same thing, but you only have 128 page faults total. Okay, so your access pattern, I mean, that's another way of saying your locality can make a big difference. So certain compilers are aware of this thing, can optimize that for you. Okay, but you should be aware that there's a limit to how much OS can do, and sometimes you just gotta rely on compiler to be aware of the cache, memory, virtual memory, the paging characteristics to make it run efficiently.